So today we're going to start our discussion of acid and base chemistry. So I've been told that you all talked a little bit about this in Gen Chem 1. We're not going to assume a whole lot of things from Gen Chem 1, but we might kind of move a little bit quickly through, identifying acids and bases. But anyway, we'll review some of this concept that you learned from last semester, and then kind of expand on that idea, focusing on determining pH. So again, if we're in a aqueous solution, the way that we identify whether typically if it's acidic or basic is utilizing pH, and sort of correspondingly, sometimes we use pOH. And then we'll put this in the context of equilibrium. So again, that's what we've been talking about before. So if we're talking about an acid or a base reaction, again, we can use a equilibrium constant expression, Ka or Kp, to talk about that acid or that base. Then we'll end class today talking about strong acids and bases. So those are typically, we don't refer to them as being in equilibrium, and therefore their calculation of the pH is a little bit more straightforward. So that's kind of where we're going today. So to begin with, we'll start pretty straightforward. So there are different definitions of acids and bases. The one that we'll be focusing on mainly here in Gen Chem is this Brown-Fitted-Lowry definition, which really tracks for us essentially how the proton is transferred. So again, it's a proton. So H plus is being moved from one species to another. So by definition, we say the acid is the species that donates the proton. So in this reaction here, I have HCl. So the proton here, my H plus, is being transferred from my HCl, my hydrochloric acid, to my water, which is serving as my base. So again, correspondingly, whenever I have an acid, I'm going to have a base in my reaction, and they work in tandem. So again, my acid is the species that donates my H plus, which is indicated in red. My base is my species that accepts my H plus. So ultimately, that is essentially what's happening in the context of our reaction. So again, if we transfer the proton from one species to another, we draw our corresponding products. So my conjugate acid is going to have one more proton than it did at the beginning. And then my conjugate base is going to essentially have one less proton. So again, really what I'm doing is these are sort of just labels for us to identify what's going on in solution. Again, sort of by convention, we typically say conjugate acid and conjugate base are my products in my acid-base reaction. But ultimately, it's a way for us to sort of determine the directionality. The way that I like to think about it, and sometimes it's hard to, especially as we're kind of getting used to talking about acids and bases, the way that I like to think about identifying what is the conjugate acid and what is the conjugate base is thinking about the reverse reaction. So again, if I'm thinking about H3O plus or my hydronium and my chloride anion, I'm thinking about the reverse reaction. My conjugate acid is going to be the one that donates the proton to my conjugate base. So again, ultimately, if I'm going in the reverse direction, my H3O plus is going to have one less proton on the left-hand side. And ultimately, my conjugate base is going to have one more proton on the left-hand side. So it helps us identify what is the conjugate acid and conjugate base. You okay with these ideas? So you may ask, why am I transferring a proton? So again, based on our Brown-Fitted-Lowry definition, we're transferring a proton. Why is it not a hydrogen atom? Well, that gets us back to some of the stuff that we talked about essentially from the beginning of this semester, where we talked about essentially how are the electrons being shared with an individual atom. So again, our general way of drawing an acid is just to label it as HA. So technically, you could think about breaking this bond in two different ways. One of the ways that we could break the bond is what we say homolytically cleave it. So we give one electron to our hydrogen, we give one electron to the rest of our acid. Or we could do heterolytic cleavage. So where we could donate essentially either two electrons to the rest of our acid or the two electrons to our hydrogen. So again, these are the possible ways in which I could break that bond to the hydrogen. So again, we see heterolytic cleavage. And again, the reason why ultimately it's an H plus and then we draw our conjugate base as A minus is because those electrons are not being shared equally. So again, thinking about how these are being shared, we'll have to look at electronegativity. So again, hydrogen is on the left-hand side of my periodic table. Remember that our electronegativity trend increases as we go from left to right. And from essentially down, up, we increasing electronegativity as we go up the periodic table. So typically, the atom that the hydrogen is bound to is usually more electronegative. So again, what we're doing is if we're transferring that particular proton, we're essentially giving extra electrons to whatever the atom that was attached to. So conceptually, we think about this, again, kind of more from my background here as an organic chemist, we think about this as what we call a proton transfer mechanism. So for me, it makes a little bit more sense to draw that. Again, you're not necessarily responsible for this mechanism, but in some ways it helps me conceptualize essentially what's happening here. So what we're doing here is this is our acid-base reaction from the previous slide. Again, HCl and water is creating hydronium and Cl-. So what I'm doing here is, again, we have a polar bond between hydrogen and chlorine. I have a partial positive charge on my hydrogen, partial negative charge on my chlorine. Again, the two electrons of that hydrogen-chlorine bond are not being shared equally. So what happens here is my base, again, is going to accept a proton, and it's going to form the new bond to that proton. So we'll go ahead and circle this as the proton that we're essentially abstracting. It's going to take these two electrons, again, it can be either of the lone pairs on this oxygen, and we are going to essentially form a new bond. So again, these two electrons here form a new bond to hydrogen, okay? And in order to form a new bond with that proton, I have to break the hydrogen-chlorine bond, right? If we think about it from our basic understanding of a Lewis-Down structure, I can only have two electrons around that hydrogen. So I'm breaking this hydrogen-chlorine bond and donating those electrons towards the more electronegative chlorine. So notice that on my left-hand side, my acid, and focusing specifically on the chlorine, has 1, 2, 3 lone pairs. Notice the conjugate base on the right-hand side has 4 lone pairs. So essentially, we've donated an extra set of electrons, essentially from this position here. So again, the reason why we're transferring a proton or H+ is based on the electronegativity difference between what the proton is attached to. That kind of makes sense. And to connect a few pieces together here. Again, you're not going to be responsible for the proton transfer mechanism, but again, for me, it helps conceptualize essentially what's happening. So why is this being donated and why is this accepting that proton? Again, our HCl is defined as our acid, our water in this reaction is defined as our base. Okay with this idea? So let's go ahead and practice. So go ahead and label the acid and base, and go ahead and label the conjugate acid and conjugate base for this reaction. And then for our bottom down here, we have ammonia. So go ahead and draw the conjugate acid and conjugate base for ammonia. Especially for this structure down here, make sure we're identifying the correct formal charge on our nitrogen atom. So I'll give you about 2-3 minutes or so. Talk about this with your table. Again, label the pieces for your top reaction and then draw the conjugate acid and conjugate base of ammonia on the bottom. Okay, so which is my acid and which is my base in this equilibrium reaction? So is my hydroxide acting OH, is it acting as an acid or a base? Yeah, it's acting as a base. So in this case, again, if we go from left to right, hydroxide is gaining a proton, so it is accepting a H+, so that is a base. And then my acid is donating H+. In this case, it's the one that's directly attached to this oxygen here. So notice as we go to the right-hand side here, we have a formal negative charge on that oxygen, 1 less proton on that acid, and then 1 more proton on the right-hand side with our corresponding conjugate acid. Again, thinking about the reverse direction, again, this is my conjugate acid, my water is donating a proton, and my conjugate base is going to accept that proton in the reverse reaction. That makes sense to everybody? Okay with these labels? Okay, so we can also talk about conjugate acid-base pairs. So we'll talk about this actually quite a bit throughout our discussion of acids and bases. So it's important for us to be able to quickly assess based on a structure, the conjugate acid or conjugate base. So again, if I'm drawing my conjugate acid, I have one extra proton. So, right, I'm gaining a proton, if essentially that's the conjugate acid. So ultimately it's going to look like this. So if I have one additional proton, I have 4 hydrogens around that central nitrogen. Thinking about our thermal charge calculation. So ultimately, what we have here is nitrogen is in group 5 of the periodic table. So again, formal charge is essentially the group that we are on the periodic table. So group 5 minus the number of lone pair electrons. So how many lone pair electrons do I have around that nitrogen? Do I have any lone pairs? Do I have any dots? No, I don't have. So I have 0 lone pair electrons around that nitrogen. And then I'm going to take half of the bonding electrons, which in this case I have 4 bonds. Again, there's 2 electrons for each of those bonds. So if I add that together, I have 5 minus 4. That gets me to that +1. I have a plus charge on that central nitrogen. Correspondingly, if I go from the ammonia to the conjugate base, again, I basically take 1 proton away. So if I take 1 proton away, then I'm going to have the opposite charge. So again, same formal charge calculation. So 5 minus, in this case, I have 2 lone pair or 2 sets of lone pairs electrons, or 4 lone pair electrons, minus 1/2 of 4 electrons, because I have 2 bonds and 2 electrons in each of those. So then ultimately, it's going to be 5 minus 6 is going to be -1. You okay with that? And just kind of quick review of formal charge, make sure we're comfortable with that. Any questions on labeling? Okay. So we have a specific label for species that can act both as an acid and base. So we call this amphiprotic. So it's just kind of a fancy term for saying, again, it can act as an acid or a base. So in this case, you can't necessarily imply that it'll act. So depending on the set of conditions, it'll act either as an acid or as a base. Okay, so let's talk about this very important equilibrium reaction. So it looks like a pretty basic reaction, or not very exciting reaction. So basically, this is what we call the autoionization of water. So I have water, and no matter what form, ultimately it's at an equilibrium. So it's at an equilibrium where it creates 2 molecules of water, create 1 molecule of H3O plus hydronium, and 1 molecule of hydroxide OH minus. So this is one quick aside. I'm going to be drawing hydronium instead of just H plus. So your book, and depending on your resources, sometimes refer to this as essentially the species here. So you can think about, if you use 1 molecule of water, it could separate into H plus and OH minus. This does not actually exist in solution. So I'm using H3O plus to more accurately represent essentially what's going on in solution. But if you see H plus, essentially think about that as H3O plus for hydronium. So is water particularly acidic or particularly basic? No. If we stick our hand in water, nothing really bad happens to our hand, right? So essentially, this equilibrium is pretty small, right? I'm not creating a lot of acid or a lot of base. So again, we could write this as an equilibrium constant expression. And again, this isn't a case where we have a heterogeneous equilibrium, right? I have my 2 water molecules in my reactants are liquids, and then I have aqueous species in my products, H3O plus and O minus. So again, we drop our pure liquid or pure solid. So my equilibrium constant expression, K, and we use the subscript W to indicate that this is the K for water, is going to be the concentration of H3O plus times the concentration of OH minus. And again, kind of what we just talked about here is, again, we don't create a lot of base or acid in solution, just in pure water. So this number is very, very small. So at 25 degrees, we have determined that the concentration of H3O plus and the concentration of OH minus is 1 times 10 to the minus 7. They also exist in equal concentrations because, again, if we have pure water, this is what we call a neutral pH. So we don't have an excess of acid or base. So again, we can actually solve for this K numerically. We just multiply those two together. We get this very, very small number, 1 times 10 to the minus 14. Hopefully this is ringing some bells. Okay, so as long as we are at room temperature, we're at 25 degrees, this relationship or this numerical value for the relationship between H3O plus and OH minus is consistent. And so we're going to use this KW a lot to relate essentially our concentrations of H3O plus and OH minus. So while this number may change if we are at a different temperature, the relationship between hydroxide and hydronium is always going to be consistent. So again, this autoionization of water, again, just based on the fact that this is the equilibrium that exists. Again, this is the equilibrium constant that we've been talking about. In this case, it's just specific to water, but this relationship remains constant when we're talking about the equilibrium of water. So again, just to kind of emphasize here, we have a equal concentration of acid to an equal concentration of base. So that is sort of by our definition, a neutral solution. So again, if we have an excess of my acid in solution, H3O plus or H plus in solution, then we would consider it to be acidic. If we have an excess of OH minus in solution, we would consider it to be basic. If those concentrations remain the same, or if they are equal to each other, then we are under a neutral solution. So again, we can look at the concentration or really the relationship between these two concentrations to help us determine whether we're under acidic, basic, or again, if they are equal neutral conditions. So oftentimes, or at least in the context of the way that we measure this in the lab, we use a different scale, right? We use typically the pH scale. Again, there's reasons for this. I don't know, people don't like scientific notation. So instead of, thinking about, sometimes it's difficult in our head to rationalize, okay, what is the exponent and what is the relative relationship, of these two numbers in scientific notation? It's easier just to look at a whole number value and determine essentially whether we are, acidic or basic. Again, we define essentially anything below 7 as acidic and anything above 7 as basic on that pH scale. We all okay with these concepts? So we got to talk about essentially how do we calculate pH, which we'll do in just a second. Okay, so again, we calculate pH based on the concentration of our hydronium, H3O plus. And really, anytime you see the letter P in front of something, assume you're taking the negative log of that particular number. So you'll see P in front of a lot of different things today in class. It's the same operation to whatever you're doing. So again, we have a P in front of H, and the H is representing our H plus or our H3O plus hydronium concentration. So again, we're just taking the natural log of that. So again, our acidity scale is directly a measurement of our concentration of H3O plus. Again, typically in aqueous solutions, we're somewhere between 0 and 14. There are exceptions to this. And again, as you get outside of aqueous-based solutions, the scale gets larger. But again, if we're thinking about this in the context of specific concentrations, going from 0.1 molar to 10 to the minus 14 molar of H3O plus. So again, if I'm 1 molar H3O plus, again, I plug that into my pH equation, take the negative log of 1, and again, we would say that that is 0 in terms of its pH, and that's very, very acidic. If I have pH, or excuse me, H3O plus concentration of 1 times 10 to the minus 14, that's, again, I take the negative log of that number, that's going to be 14, that's kind of the basic end of my solution. Similarly, I can figure out if I'm given, so this is if I'm given H3O plus concentration, I can calculate pH. I can go in the reverse direction to determine H3O plus, because sometimes that's important for us to be able to do. So to basically get rid of this negative log, what we do is we take the base 10 to the negative exponent. So again, if I want to go from pH to H3O plus, I'm going to take 10 to the minus pH. So again, make sure we're incorporating that. So an example of what that would look like is if I have a neutral pH, a pH of 7, again, my H3O plus concentration is going to be 1 times 10 to the minus 7. Again, I can get that by plugging it into this equation where 10 to the negative pH, so 10 to the minus 7, is going to get me to that neutral solution or neutral concentration for H3O plus that we talked about with KW. We all okay with these ideas? I'm going to practice on the next couple of slides. So any questions before we practice? Okay. So let's work on this question. So what is the pH of a solution with a concentration, hydronium concentration of 6.5 times 10 to the minus 9? And is the solution acidic or basic? About a minute and a half to work on this one. Okay, looks like most of us got the right answer. So again, really, we're just utilizing the equation for pH. Again, we're given the concentration of H3O plus. That's essentially our direct measurement of pH. So we plug that into the negative log of this equation, and we get the value 8.19. So it's basic. So again, since we are above 7, it's basic in solution. So just a quick aside about sig figs. So once we started incorporating logarithms, ultimately our analysis of significant figures changes a little bit. So ultimately, what we do is, if we are given, so we're given 2 significant digits in our concentration of H3O plus. So the way that we express that within, again, if we're taking either the log or the natural log of something, we express that as the number of decimal points. So in this case, since we have 2 sig figs in our concentration, we're going to have 2 decimal points where we're going to have essentially to the 100th place in our pH calculation. And I'll try to be a little bit generous with these because the rules are a little bit strange, but just to kind of talk a little bit about sig figs. Okay with this calculation, this idea? Okay, let's continue to practice. So if I have a pH of my solution is 3.5, what is the OH concentration for that solution? And you've got 2-ish minutes. Okay, so let's talk about this one. We're less successful on this one. So again, what we're doing is we're taking, we're given the pH. So we ultimately need to convert this into our concentration for H3O plus, and then utilizing that relationship between the concentration of H3O plus and OH, we can correspondingly calculate the concentration of hydroxide. So let's go ahead. The correct answer is C, but let's walk through how we got there. So again, we're given our pH. So again, what we want to do is convert into H3O plus because we have that relationship between H3O plus and hydroxide based on our KW. So again, KW is going to equal the concentration of H3O plus times the concentration of hydroxide. So again, we need to take this pH and convert it into the concentration of H3O plus. And again, we do that by utilizing this equation. So 10 to the negative pH. Okay. So if I plug that in, so 10 to the negative 3.50 is going to equal, so let's go ahead and do that. So 10 to the negative 3.5 is going to equal, I'm going to carry some extra sig figs with us just for a good measure, 3.1623, I guess, times 10 to the minus 4. Okay, so this is again is my concentration of H3O plus. So again, the question is asking me what is the concentration of hydroxide. So again, I'm going to rearrange this KW equation to isolate essentially the value that I am interested in, that hydroxide concentration. So to do that, again, basically what I'm going to do is just move the H3O plus concentration over. So divide both sides by H3O plus. So that gets me this relationship. So the concentration of OH minus is going to equal KW over the concentration of H3O plus. Again, we just calculated the concentration of H3O plus as this number, and Kw, again, as long as we're at 25 degrees Celsius, so you can assume, unless you're given a different temperature, you can assume that we're using this value of 1.0 times 10 to the minus 14 for Kw. And I'm going to divide that again by that number that I just calculated. So we can go ahead and plug that into our calculator. So 1 times 10 to the minus 14 divided by the number. And that's going to equal 0.316 for our value for our concentration of OH minus. Does that make sense to everybody? So again, going from pH to H3O plus, and then utilizing our Kw relationship to go from H3O plus to hydroxide concentration. Yeah.
What did you say the right answer?
Did I have the wrong answer? So it's, let's go ahead and hear the option. Oh.
Yeah.
Oh, whoops. Oh, that's why. Okay. Whoops. Okay. Let's flip that back. Sorry about that. That's why. Okay. Okay. So it'd be 1 times 10 to the minus 14 divided by, again, that number 3.1623 times 10 to the minus 4. Yeah. So it should be a much smaller number. Oops. Sorry about that. Just plugged in my calculator wrong. That happens. So 3.16 times 10 to the minus 11. Because we have a very small number divided by a larger number, so that's going to be exponent there. Okay, does that make sense? So actually, we need to talk a little bit about sig figs as well. So if we go basically in the reverse direction, so if we take our 10 base log, essentially, again, we have 2 digits after the decimal point. That is limiting the number of significant digits in our concentration answer. So it's kind of the reverse of what we just talked about here. And again, I'll be generous with the sig figs because the units or the analysis for this is a little bit tricky. Are we okay with how we got there? Okay, so again, we mentioned before when we were calculating pH, again, whenever I see the letter P in front of something, I can assume I'm taking the negative log of whatever that is. So we can take the pH, again, looking at the negative log of the concentration of hydronium. We can also determine the POH. It's usually less frequent. We don't use POH as much, but again, if we're in a basic solution, again, tells us the relative strength of that basic solution. So it's used occasionally. So again, the way that we would determine both of these. So again, we'll just plug this into a particular example where, again, if I'm at that autoionization of water from that neutral pH, again, my concentration of my acid, H3O plus, is going to equal the concentration of my base. Again, assuming we're at room temperature, we have these values of 1 times 10 to the minus 7. So again, if I plug that into both of these equations, I get the same number, right? So again, I get 7 for the pH and I get 7 for the POH, and that's essentially defined as neutral on both of these scales. From there, ultimately, we can also take what's called the pKw. So again, if you don't want to deal with scientific notation, again, we can take the negative log of our Kw value. So in this case, again, that value is 1.00 times 10 to the minus 14. So ultimately, that can equal 14. So we can re-express this basically in this relationship here. So again, instead of using Kw and Ka and Kb, we can write this utilizing sort of logs. So again, moving away from scientific notation to whole number values. pKw is going to equal the pH plus the POH. So again, at neutral solution, again, 7 and 7, it's going to equal 14. So again, we can also solve the previous problem that we just talked about utilizing this equation if we would like. You can calculate pH and convert it into POH, and then calculate the concentration of hydroxide based off of that. So again, just a slightly different way to approach this. Basically, instead of using scientific notation, we're using the P connotation to use whole numbers. You okay with this idea? So again, this is just kind of just putting this into a little bit larger context. So again, typically in the lab, we would have some sort of pH meter. So again, use your probe and you typically calculate pH. Again, most probes you can also toggle to pOH if you want to do that. But again, this is kind of our general scale. So again, as we decrease in pH, we are becoming more acidic. As we increase or decrease in pOH, we become more basic. So again, depending on what you're analyzing, whether it's a basic or acidic solution, you can toggle between those. Again, we can also use the concentration of H3O+ or the concentration of hydroxide to determine essentially acidic or basic solutions as well. So again, depending on the context, we'll pick one of these variables and utilize them to represent the relative acidity or relative basicity of our solution. Okay, so let's talk about this in the context of focusing now specifically on an acid. So again, given this particular expression, so this is what we call our equilibrium constant expression for an acid. Or for acid dissociation, or Ka. So again, it's an equilibrium constant because we have the capital letter K. The subscript A is telling me that this is an acid reaction. So let's go ahead and write the Ka for this particular reaction. So what is the concentration relationship between my reactants and products? Give me about a minute or so to write that out. Okay, so our Ka expression is going to look like this. Again, we have a heterogeneous equilibrium. Again, we're assigning our acid and our base, conjugate acid and conjugate base. So again, typically the sort of general way in which we define an acid is we write it as HA. So again, A is some other part of the molecule. That obviously can change, but we are adding that to water, and then we produce our conjugate acid. So again, our species that has one less proton. And our conjugate base is always in this expression going to be H3O+. Okay, so our Ka expression is going to look like this. So concentration of H3O+ times the concentration of my conjugate base, A-, over the concentration of HA. Again, we drop the water in our solution because it is a pure liquid. So again, we've been talking a lot about calculating or defining this in sort of a P-log category. So again, we can take also the pKa, we can apply the P to the Ka expression as well. So again, that can help us basically taking out our value from scientific notation to whole numbers. And again, typically pKa is what in organic chemistry we typically use to define the relative acidity of something, but you can talk about both of them. So again, this is our Ka expression. So again, our equilibrium constant for acid dissociation. So again, water is going to be our other species with our acid, and then we're always going to have H3O+ as one of our products. So from here, give about a minute or so, talk about this with your table, determine a higher Ka value is going to result in a stronger or weaker acid. A higher pKa value is going to result in a stronger or weaker acid. So talk about this with your table, figure out what kind of scale we're on in terms of Ka versus pKa, and which defines a stronger or weaker acid. So again, as we increase what species, what makes something more acidic. So if we look at our equilibrium reaction here, what concentration am I increasing to make it more acidic? What did we just use to measure pH? Yeah, H3O+. So as I'm increasing the H3O+ concentration, that is making me more acidic. So then how do I apply that to Ka and pKa? Okay, so what do we think for our Ka? If I have a higher Ka value, do I have a stronger acid or a weaker acid? Or another way to say this is, as I increase my Ka, is the acid becoming stronger or weaker? And why? Stronger, yeah, why? Yeah, exactly. So in this case, again, we're measuring P. If we say pH is increasing with our increasing H3O+ concentration, then ultimately, or decreasing, ultimately, as I increase my H3O+ concentration, my Ka value is going to get larger, right? So as I produce more and more of my products, my Ka value gets larger. Okay, so a stronger acid. it's not always super intuitive with this negative log of this, but ultimately it's going to be the opposite direction for our pKa. So again, you can solve this or kind of rationalize it to yourself by plugging in two different values. So you can take the negative log of 1 versus the negative log of 10, and then basically determine the trend based off of that. So again, as our pKa gets smaller, or it gets larger, excuse me, our acid becomes weaker. And typically our pKa values range, a much larger range than our Ka values. So typically are from, I don't know, -7 all the way up to 50. So again, our negative numbers are going to be more acidic than our higher numbers. Okay, so let's go ahead and, whoops, forgot the animations for this here, but let's go ahead and draw the products for this reaction here. So go ahead and draw the products for our strong acid, HBr in solution. So if I mix HBr with water, what are my products going to be? Okay, so my HBr is serving as my acid in this reaction. So again, as we go from our acid and base. So again, our acid is donating a proton, H+, to our base, which is water. So again, water is going to be our conjugate acid. It's going to have one additional proton. Br- is going to be my corresponding conjugate base. So HBr is the example of a strong acid. So we define a strong acid as completely dissociating in water. And what we mean by that is all of my HBr is converted into products. So functionally, I have no HBr in my solution. So again, we can kind of put this in the context of sort of an ice table. We've talking about this in equilibrium. This isn't exactly an equilibrium reaction because again, we're just producing products. But if I have a 0.5 molar solution of HBr, again, all of that is essentially going to be converted into my products. I have a one-to-one relationship between my reactants and products. So again, I produce 0.5 molar H3O plus and 0.5 molar Br-. So again, functionally, I have no HBr left in solution at the end. So again, these are what we're defining as our strong acids in this class. So the three are kind of easy to remember. Those are three of the halogens. So HCl, HBr, and HI are strong acids. And then perchloric acid, so HCl4, nitric acid, HNO3, and H2SO4 are sulfuric acid, we're defining as our strong acids. So these are ones that you'll have to memorize. So just make flashcards, know that these are our strong acids in solution. So again, our definition of our strong acid is that it is completely creating our conjugate base and H3O plus. Again, no HBr, none of our strong acid remains in solution. So if I have a strong acid, is my Ka value going to be high, low, or not enough information? High, yeah, it's going to be very high because ultimately, again, I functionally don't have any of my reactants remaining. I just have products. Again, if we're talking about an equilibrium constant, we're talking about the concentration of our products over the concentration of our reactants. We're going to have a very, very high Ka value for this. Or again, if we're talking about pKa, we're going to have a very low pKa value for this. We okay with this idea? We're going to practice on the next slide. Let's go ahead and practice. So what is the pH of a 0.5 molar solution of HBr? Okay, so it's like almost all of us got the correct answer. So again, if we are taking a look at, this is basically, if we look at this example here, again, HBr, strong acid in solution, we're converting all of that HBr into H3O plus and Br-. So ultimately, we are creating the concentration that we have initially of our acid, we're creating that concentration in H3O plus. From there, ultimately, we just have to plug our concentration of H3O plus into our pH equation. And if I take the negative log of 0.5, that gets me to this pH of 0.301. That makes sense, everybody? Okay. So let's talk a little bit about bases. So again, we can define our general base reaction or our equilibrium constant for base protonation. Again, utilizing sort of our general expression for this here. So ultimately, oops, have those switched. So this is going to be my base, this is going to be my acid. Sorry about that. So my minus here is ultimately my base. So again, this is any sort of base reacting with water. Again, the base becomes a corresponding conjugate acid, and we create hydroxide in solution. So again, this is what we call essentially our base protonation. So again, this is just the general form of that. So I'm always going to have water as one of my reactants with my base. That's always going to create a hydroxide and my corresponding conjugate acid. So again, let's go ahead and write the equilibrium constant expression for this reaction as well. So what is the Kb for this? Okay, so our Kb looks like this. Again, we're dropping our H2O. Again, that's our liquid in solution. So pure liquids don't appear in our equilibrium constant expressions. Don't know why this is H with subscript A. That's HA as our concentration of our conjugate acid times the concentration of hydroxide as our conjugate base over the concentration of our initial acid. Again, similarly to what we did for Ka, we can take for Kb, we can also take the pKb. Again, just taking the negative log of that particular expression. So again, essentially, the higher the Kb, are we going to have a stronger base or a weaker base? Anyone want to tell me? Yeah, so we're going to have a stronger base, right? We're creating more hydroxide. So as my numerical value for my equilibrium constant increases, again, ultimately, my concentration of hydroxide is the way that we measure our base. As that increases, that K value is also going to increase. So again, we can take the pKb. Honestly, we don't really use the pKb all that often. But again, just we're taking the negative log of that expression. So just to be familiar with, that's essentially what that represents. Again, typically we talk about the pKa values, the acidity values, more than we talk about the base acidity values. We okay with this idea? Okay, so similarly to strong acids, strong bases completely dissociate in water. So again, we're taking typically our solid species, our solid, again, the strong bases are a little bit easier to remember because essentially they are our hydroxide bases. Again, as we increase the concentration of hydroxide, we are making our solution more basic. But again, thinking about this from sort of balanced chemical reaction, and I'm throwing that solid into solution, I'm creating my cation, whatever that is, whether it's lithium, sodium, potassium, and then my hydroxide in solution. So again, based on our definition here, we do not, or this completely dissociates in water, or we don't have essentially any of our strong base remaining in our solution. So in terms of calculating the pH, this is going to be the same sort of relationship where, again, I'm assuming that all of my initial concentration of my base is converted to hydroxide. So again, we can use the same sort of relationship. In this case, we therefore know the concentration of hydroxide. And we can use one of these expressions, whichever you feel most comfortable with. Again, we can use the concentration of hydroxide to measure the concentration of H3O plus and then calculate pH, or we could take the hydroxide concentration, convert it into POH, and then convert it into pH. So again, there's technically sort of two different ways in which we could accomplish this. But again, strong acid, strong base, we assume they completely dissociate or everything is converted into products. You okay with that idea? Okay, let's go ahead and practice them. So what is the pH of a solution of 0.6 molar sodium hydroxide? I'll give you a few minutes. Feel free to, oh, I guess I gave you the answer. So, well, let's just work through it. That's fine. So there's two different ways in which I can determine this. So the two different ways in which I can determine this relationship is by, again, utilizing either the P8 or the POH and pH relationship or my KW expression. So let's walk through the two different ways in which we could solve for this. So again, if we're thinking about sodium hydroxide, again, all of the sodium hydroxide gets converted into its corresponding ions. Again, that's what we mean essentially by it being a strong base. So again, my initial concentration of my sodium hydroxide. So again, if we think about this sort of through the language of an ice table, I have 0.6 molar sodium hydroxide and essentially nothing as I begin the mixing process. Again, based on the fact that this is a strong base, all of my base gets converted into my corresponding products. So again, it looks like this. So I functionally have no hydroxide, sodium hydroxide remaining. I just have the corresponding ions in solution. And again, we're utilizing this hydroxide concentration ultimately to measure our pH. So again, I said that there are two different ways in which we could solve this particular problem. So the two different ways are, the first way, I can use essentially the POH and convert that into pH. So again, I have my hydroxide concentration here. So again, POH is the negative log of my hydroxide concentration. So in this case, I can take the negative log of 0.6. So just take the negative log of 0.6. That's going to equal 0.222, if I round this correctly, so 0.222. Then from there, again, the relationship between POH and pH is related by pKw. So pKw equals POH plus pH, and that number equals 14. So again, basically just taking the KW relationship and converting it from our scientific notation to whole numbers. So again, if I'm interested in pH, I want to isolate that particular term. So pH is going to equal 14 minus POH. And we just solved for the POH previously. So 14 minus 0.222. So my value equals 13.778. That is one way in which I could solve for the pH. The other way is essentially utilizing the initial OH concentration. So again, converting that OH concentration into hydronium. Again, that relationship is defined by KW. So KW equals my hydroxide concentration as my hydronium concentration. That equals 1.00 times 10 to the minus 14. So again, we're given our hydroxide concentration, or we determine that based on the fact that we have our strong base. So again, we can rearrange this equation to solve for H3O plus. In this case, it's going to be the concentration, or KW, over the concentration of OH minus. So that equals 1.00 times 10 to the minus 14 over this value here of 0.600. So I plug that into my calculator, I get 1.6 repeating times 10 to the minus 14. That number makes sense, right? Since I have a strong base, this value for my hydronium concentration is going to be small, right? I don't have a lot of my acid if I'm in a very basic solution. And then from the concentration of H3O plus, I can calculate pH directly. So again, pH is the negative log of my hydronium concentration. So I'm going to take the negative log of 1.6 repeating times 10 to the minus 14, and that should get me the same value that I saw before, 13.778. So again, either of these approaches can get you to the exact same answer. Any questions on that?
So with the remaining minute that we have, what I want you to do is just kind of summarize. So I have a quick question for you to summarize in your notebook. What are the different ways that in which you can know that a solution is acidic? So again, just take about a minute or so, jot down the different ways in which you can determine whether your solution is acidic in your notebook, just to kind of help you summarize all the different concepts that we talked about today. Yes, lots of different answers. There's no one right answer.